Welcome to this introduction to networking. I will be splitting this introduction into three parts. For these lectures, I will be using a slide set, or at least some slides from a slide set created by Jim Couros and Keith Ross at the University of Massachusetts. So they are famous researchers in networking who have written a textbook that is now in its 8th edition called Computer Networking, a Top-Down Approach. That's the book that I am usually using when I teach networking. Um, so I will be drawing from the slide set here as well. I really like this book and I recommend it. And also recommend that you take a course in networking. What I like about this book is its top-down approach. Now, top-down here means that unlike traditional networking books, which start with the low levels of how data is transmitted across links, this book starts with the applications, network applications that we all use, and from there works its way down through the networking stack, talks about the transport layer protocols, network layer protocols, and then discusses the individual link protocols last. What that means, I will hopefully will make sense shortly. So, part one, the internet with a capital I. What is the internet? Okay, so different ways of looking at it. Of course, you all know what the internet is, but let's break it down and be a bit more concrete. So, a nuts and bolts view of the internet rather, is that it's the billions of connected devices, right? They have a name and they are called hosts. Okay, you get the pen. They are called hosts, or in some cases they're called end systems. Okay, end because they're at the edge of the network. And network applications in the internet run on these hosts. Okay, at the internet's edge. That is part of a fundamental design principle that the internet uses, which is that the network is quote unquote dumb, and that the application logic is located at the edge of the network. That has been a very successful design principle. So, what's inside the internet? Well, there are so-called packet switches that forward data through the network. Data is split into chunks, which are called packets. It's a generic term, although we will see that there are more specific terms at different um layers of the networking stack, but let's call them packets for now. These packets are sent through these switches, and also more concrete terms for certain types of them, such as routers and also the term a switch. These switches are connected to each other through communication links. Those may be based on different physical media, such as fiber, copper, or it may also be radio links or things like um, Wi-Fi, wireless access networks. Some of them may be using satellite. A key characteristic of a communication link is its bandwidth or transmission rate, the rate at which it can send bits. Now, the internet, turns out, is not a single network, but rather it is a group of networks that are connected with each other. So a network itself is part of the internet. It's a collection of devices and routers and links that are typically managed or owned by one organization. And these networks are interconnected to form what we call the internet. And lots of devices connected to it, some of which here are shown by the textbook authors, from medical devices to like fever thermometers, for example, to all kinds of things that we have all grown to use. So the internet is a network of different interconnected ISPs. ISPs are internet service providers. Okay, so these are providers that provide internet service to their clients. The exchange of information of data between them is guarded by protocols, and protocols occur everywhere at all layers of the networking stack to do different tasks. Examples include Skype, and a protocol that allows video conferencing. IP, that is just a protocol that's in charge of making sure data gets through the network. HTTP, a protocol that you know to retrieve web pages. Um, t- um, TCP is a protocol that we'll learn about to make sure that data can be transmitted reliably. And then Ethernet, the protocol that is used to when you for example plug into a port in your office or on campus on the Torgerson Bridge. There are Ethernet ports. There are lots of protocols everywhere, and the internet is somewhat unique in terms of how many of these protocols are being developed. Not all of them, but a fair number of them. The way this works is through so-called RFCs. So an RFC is a document that somebody can put out and say, here's an idea, here's a proposal for how to do things. Okay, please comment on it. Now, this is somewhat understated because it's really saying, adopt my way of doing things and maybe do something in the same way that I'm doing so that we can then interact with one another. But that's the mechanism. And so everybody can put out an RFC. Okay, there's no red tape. Now, one of two things then happens. Either people just ignore it, they don't like it, we don't want to do things your way, then in which case the RFC just expires. But if RFCs are being taken up by others, they may become de facto or standards. And this is the process by which the internet has grown historically. Everybody had the right to put out an RFC, and it either was adopted or it expired. Now, more recently, a more formal process was put into place where the IETF, the Internet Engineering Task Force, actually started discussing some of these RFCs, and some of them were then elevated to the status of an actual internet standards. But those were typically protocols, specifications that had originally come out as RFCs and that had been in wide use for a long time. We can also view the internet in terms of the services that it provides. So it's an infrastructure that provides services to applications. Okay, the examples include streaming video, the web, multimedia teleconferencing, and so on. These are really applications that are programmed to run on top of the internet. Okay, so that they provide a service to user, and the internet provides a service to them that allows them to exchange the data that they need to exchange to provide their own service. So here the internet can be viewed as providing a programming interface to these distributed applications. So it needs to provide entry points, hooks, that allow these applications to send and receive data, as well as to connect to their counterparts or peers on the machines that they wish to connect to in order to provide a service for a user. I mentioned a protocol a number of times. What is a protocol? We are the protocols from human interaction. Okay, so an example is, how do I go about asking someone the time, right? Let's say if I don't have my phone with me or so, or I want to ask a question, someone, or maybe you want to ask a question in an actual classroom settings, right? There's a certain protocol, a certain way to go about it. For example, to ask a question, you would typically raise your hand, right? Then you would wait to be called on, and you ask your question, and then hopefully you would get an answer. Introductions between humans, people, is another example. So this typically involves some agreement on what messages should be sent and what action the receiver takes upon receipt of these messages. And it is the same with network protocols, except here the parties are computers or devices rather than humans, and these protocols are more formally specified in these RFCs that I mentioned earlier. So more precisely, protocols define the format and the order of those messages that are sent and received among the participating network entities, and also the actions that they take when they receive some of these messages, in some cases also when these messages are being transmitted. An example. A human protocol, that is example of what's the time, you may say, instead of just blurting out, hey, what's the time, you would start and create contact by saying maybe hi. And then the party you're talking to, they may also say hi, indicating that they are ready and willing to talk with you, or they may not if for whatever reason they don't have the time or don't want to. But after they say hi, then that's the green light for you to then ask the question, what time is it? And hopefully get a response. Similarly, a computer network protocol that retrieves a web page wouldn't start out and sending, okay, give me that page. But first, a connection has to be created. So in this case here, a TCP connection request is being sent and a TCP connection response is received before a computer can ask to send a request to retrieve a web page. In this case here, so-called GET request for a specific web page that is then responded to with the file that contains the data for this particular web page or object. That's an example of a simple protocol, but it gets the message across. Let's take a look at the structure of the internet. And specifically here, let's talk about what happens at the edge, and as well as some of the principal mechanisms inside the network, as well as its organizational structure. Okay, so here at the edge, we have these host systems that I mentioned, and host systems are often grouped roughly into clients and servers. We'll talk in a second about what these terms mean. Okay, so um, the the term client and server is in fact overloaded and used in a number of different contexts. So if in doubt, you have to ask specifically what is meant by client and server. When client and server is used in the context of connection-oriented protocols, like I showed earlier, then the client typically is the party that initiates the connection. Okay? And the server is the party that waits for connections, that waits for others to approach it. When the term client and server is used at the application level, then typically the client is the party that requests something. Maybe at the layer of the HTTP protocol, the client is the party that requests a website or an object on a web page. And the server would be the party that provides it. Now, when we talk about clients and servers in terms of end hosts, like here shown on this slide, the servers are machines that are often stored in data centers, um, like here, and clients maybe are other machines at the network edge. Then in this case, a client is used as a term for a computer that mostly runs programs that act as application level clients. And a server is a computer that mostly runs programs that act as application level servers. But it's not to say that computers cannot run a mix of both. And in fact, it's also possible that within a protocol, a client may be the party that creates a connection, but subsequently the party that's being connected to, maybe they're actually the one that requests something. So the design here can be flexible, but these are typical terms for what client and server means. If in doubt, you should ask specifically what does it mean to be a client or a server. So at the edge, we said these clients and servers. Now, the next step to the next part of this are networks that connect these end hosts to the internet. And that happens through so-called access networks. They're associated with some communication links that go over some kind of physical medium. And then the core of the internet, these are connected in some way. I want to show you examples of both and discuss some of the issues that can arise in either context. So let's first talk about the notion of bandwidth or link bandwidth. Okay, so when a host sends data across a link, let's say an application message, this message is typically split into multiple chunks called packets, each of a certain length. And these packets are then being sent. They consist of L, this may be a maximum or constant size bits, and these bits are then being sent across this link at a certain rate. And this rate is denoted in bits per second, also referred to as link capacity or bandwidth. And based on these two numbers, we can take their quotient and we can compute the time it takes to transmit a packet. It's called the packet transmission delay. Okay, the time needed to transmit an L-bit packet into this link, and it's the quotient between those two, and this is measured in seconds. So the bandwidth determines the transmission delay, but we will see that the transmission delay is actually only one of multiple sources of delay that determine the latency, the amount of time it takes for data to be sent through the network. But it is an important measure, and some of the links that I'll be talking about will be, mentioning their bandwidth in this case. So what are some of these links? So this is not a class in electrical engineering, so I'm just mentioning some example here. Principally, they can be grouped into two groups, guided and unguided media. Okay, so guided media here, examples would be based on copper or optical fiber or coax cable. An example is here shown on the right. This is called twisted pair wiring. The blue here, these are so-called category 5 Ethernet cables. They can be used for Ethernet up to 1 gigabits per second. To do run faster gigabit Ethernet 10 gigabits per second, you would need some more expensive cable called category 6 cable. Category 5 cable, by the way, is the one that is used in most professional um, um, outlets, venues. Um, for example, campus at companies and so on, with the notable exception of the Math Emporium, which still has old Category 5 cable that is actually limited to 100 megabits per second because of when it was built. Other examples I mentioned, coax optical fiber is a widely used physical media, but we also count wireless links here. Okay, so Wi-Fi satellite links as other example of links. Okay, each is characterized by a certain bandwidth. So what about these access networks? Okay, so how do these end systems connect to an edge router? So edge router here would be, this would be the edge router that these end systems connect to. Oh, I'm sorry, actually the edge router in this case would be this here, not this here. Um, and this is the access network that the different hosts connect to. Different examples of this I want to talk about briefly. For each, we should ask the question of what's the transmission rate that is possible, and whether the access network allows shared or dedicated access for users. So one example that is I'd like to talk about is so-called cable-based access. That is widely used in the United States for residential neighborhoods. Why? Because in the last half of the last century, most homes were provided with cable television, right? And so the cable provider ran this coax cable to different homes, either above ground or underground. And so every home has access to this. That is a shared network. So it's the same strand of coax that connects all the different homes in this case. And they're connected to what's called the cable head end. The cable head end is, to put some cabinet or box in your neighborhood where this cable ends, is terminated, and from there it connects to the rest of the internet. So this is a shared medium that transmits both cable television as well as the data that you use to send and receive your internet traffic. In fact, traditionally, this was used for analog television. And so this is done by dividing the frequency spectrum into so-called channels, each 6 megahertz wide. And traditionally, it was the case that each of these channels would carry one television station. Okay, this was before the advent of digital television, where now these channels set aside for television are also used for digital formats, but still for television purposes. So now here, certain channels are now being used for data, and some are used for video, and a certain number of them can be used for sending data upstream. Upstream means from any of the homes to the head end, or downstream in the other direction. So this is called an HFC, or hybrid fiber coax. Now, where's the fiber part? The fiber part is what is connecting the cable head end to the rest of the internet. This part here is the coax part. What happens if the number of subscribers grows too large so that the shared bandwidth here cannot accommodate them? In this case, your ISP should be splitting this, it's called splitting this node. In other words, run additional fiber closer to this neighborhood, split this in half, so now one group and another group of homes will have a separate cable head end. Of course, provider only does that if they have to, because it costs money to do that. There's also something else that needs to be going on. So this is a shared medium. That means only one unit can be transmitting at a time. Okay, so within one channel, okay, there's either a transmission by the head end to these homes, or one of these cable modems can send data upstream. It's not quite the case that it's just one, because some protocols also use something called code division multiplexing, where multiple modems can be sending at the same time. But in this case, the information sent by the different modems has to be separated afterwards. And there are different protocols that have been used over the years, but fundamentally, it is the case that the available bandwidth is shared by all the different participants here. And so this required some trade-offs. For example, one question is how many channels should be allocated for upstream, how many channels should be allocated for downstream. Yeah? I'm showing you the status space of my own cable modem here at home that shows the situation in our neighborhood, where my modem uses 4 channels for downstream. And these are bonded together so that that part of the data can be sent on different channels simultaneously. Otherwise, it would be limited to, I think, about 30 in the 30 megabit or so per channel, I think. Um, I have an older cable modem here that only supports 4 channels. These days, it's between 8 and 16 that can be bonded. And a cable plant provider may dedicate up to 32 channels or so, or to downstream data. Okay, because why downstream data? There's more data that goes downstream. People watching Netflix at home then goes upstream. In the upstream direction here, 4 channels are being dedicated for the different cable modems to send data upstream to the head end. Now, so far I said that treated the homes that are connected there as individual end hosts, but we all know that's not the case, right? So at home, you have an additional access network, which is your home network. So there is typically a cable or DSL modem that connects to this cable head end, or as a central office here in the case of a DSL network. And then inside your home, you have an additional network, right? You have a so-called router that provides access to devices in your home. And this could either be through wired Ethernet, or it could be through some wireless network. Okay? You may have a wireless access point um, that different clients can connect to. Okay? I want to show you a picture that I took in my garage of my own structured wiring cabinet. Okay, so here I have a gigabit switch, and then I have a cable modem that connects to it, and then the wiring here, this patch panel, runs into the different rooms of my house. I have the wireless access point actually at a more central location in the house to get better service. Actually, I have 3 of them. So last no two more examples of access networks. Okay, so wireless access networks, right, are also access networks, right? So in this case, we have these so-called access points that provide service, and then the unguided medium, the spectrum here, is also a shared media that has to be to which access has to be managed. And so this is the subject of MAC, or media access control, and there's a whole group of technologies that can be used to manage access by multiple potential senders to a network. So Wi-Fi, different standards that I used here are governed by IEEE. So there's the IEEE standards. 802.11 is the traditional series, and has various lowercase letters B, G, N, to name some, with ever increasing bandwidth. So those have been phased in over the last 25 years, starting with 802.11b, and these days it's N, and that's called AC, with a bandwidth that go up to, let's say, up to half a gigabyte per second now. Then there are also access networks that are based on cellular networks, right? So if you use data on your phone, as an example, then you're connecting to a cell tower, and you're using protocols and go by names such as LTE, 4G, or a few years ago it was 3G, and in 2020 and following years we might see the deployment of something called 5G, so new generations of these protocols to implement these access networks. What about on campus or in companies, right? So enterprise networks typically are based on a technology called Ethernet. Okay, so this Ethernet is based on this twisted pair wiring, typically, although Ethernet technically could also be run over optical cables. And so, for example, our campus is networked in this way. It has a backbone connecting different buildings, and each building has wiring cabinets that run Ethernet cables into the different offices and classrooms, into the different wireless access points. So typically, it's a mix of switches and routers that connect these and to wired ports as well as wireless access points. Okay, bit of history. Virginia Tech actually was one of the first campuses in the United States to have a campus backbone that used Ethernet, and this was in the late 1990s. Okay, and this was in fact before Ethernet became the dominant technology to build backbones on campus. Prior to that, Ethernet had been mostly technology to run networking into different offices. So what is going? So after having finished the discussion of access networks, let me talk about what's going on in the network core. There are two things that are really important to know about, and they relate to how the packets here are being routed, forwarded through the network. Okay, so when a packet arrives at one of these routers, this packet needs to be sent towards its destination. Okay, and this is called forwarding. Okay, that must be done across the links that form the path from the source to the destination. Okay, so if a packet, for example, is sent from here to there, then this router has to forward it from along the path to the next hop and so on, okay, to the destination. When a packet is being forwarded, by the way, then along this link, it is sent at the full bandwidth of that link, right? So it's transmitted full link capacity. How does that process work? There are two key functions that are here at play, and they interact with one another, but they are distinct from one another. The first one is called forwarding. Okay. So forwarding is the process when um, a, a packet switch or router receives a packet. It will need to determine to which of its outgoing links to forward the packet to. And it does that by looking at some information contained in the packet, typically in the header, a sequence of bits, and it uses these bits to look up an entry in a local forwarding table. For example, in this example, if the header contains bit 0111, then the local forwarding table may have an entry that says 0111 needs to be sent to output link number 2. So then this packet will be sent out this output link. So moving arriving packets from the input link to the appropriate output link, that process is called forwarding. It is a local action that each router has to do by itself without talking to other routers how to do that. And it uses information contained in the local forwarding table. Also, this forwarding has to happen, we say, at line speed. So this has to happen at the speed with which these packets are being sent and then received and sent, so that there is no delay due to this lookup process. Now, how do these routers know which link to use for a particular packet, right? That is the subject of routing algorithms. So routing algorithms or protocols involve an exchange between these routers, okay, where they agree on where to send packets based on their address. And so these routers have to learn the topology. They have to learn which path packet should take to reach their destination. Okay? So this is a global action that determines the path that should be chosen to be taken by a packet based on its source and destination, mostly based on the destination. And that makes it so that each router can populate their local forwarding table to put in those entries to where to send these packets. As a side note, these forwarding tables, in fact, need to contain enough information for every possible address on the internet. And so you can see that these local forwarding tables cannot have entries for individual devices. they have to have entries that apply to large groups of devices. In fact, they're being addressed by so-called network addresses. More specifically, they use prefixes. Okay, so prefix of the address, so the bits that they have in common at the beginning, is used to look up an entry in this forwarding table and then decide on the outgoing link. But fundamentally, the entire address space of the internet is covered. I'd like to include an example here that I added to the slide set to explain how this works using the analogy to zip codes that you're familiar with, right? So you may know that the zip code system in the United States uses a 5-digit code, and the entire country is subdivided into different regions. Well, these regions are subdivided such that the first digit forms a contiguous region, and so does the second one. So, for example, all zip codes that start with a 9 are located at the West Coast. A zip code that starts with a 2 is here part of the Mid-Atlantic seaboard, right? And then within those, the subzip codes like where we are here, 24, is again forms a contiguous area. So, for example, if somebody wants to send a letter from the West Coast to the East Coast, and the zip code is 24 whatever, all they need to look at is the first digit, a 2, and they know which outgoing link to send it to send it along. So maybe here to send it on whatever train, plane, or truck leaves the West Coast and is heading east. Right? And then as it gets closer to destination, additional digits may need to be looked at. So this is somewhat simplified how things work. Of course, this is today keeping track of 10,000 zip codes is no longer an issue at all. We can just store all of them. But in the case of the internet, that is not possible to store all the billions of addresses. So the prefixes here are indeed necessary to ensure efficient routing. So talked about that the internet is a network of networks, right? Where we have these access networks. And now the question is, how are these access networks connected with each other? After all, we expect to have connectivity to everywhere, right? We expect to be able to send a packet to any destination on the internet, and we want this packet to reach its destination. So how are these networks connected with each other? So how can millions of access ISPs be interconnected? So naive approach may be to just have a peer-to-peer connection, but that clearly will not scale as it would require a number of connections that would go with the square of the number of access networks. Instead, what to do instead? Well, one thing we could do is to have a network that spans the globe and have this network run by some ISP to which the different access networks connect. So for one to reach the other, they would have to go to an edge router in this global ISP, who then routes traffic to another edge router that then goes to this access network. In this case, there is an economic agreement. So typically what happens is that a smaller ISP that runs an access network may pay the larger ISP to carry its traffic and to make sure the traffic destined for it is sent to it. Now, in a market-based economy, of course, then there could be more than one of these, right? Multiple ISPs, and competitors could arise. In other, this is not the case in all countries. In some countries, there is in fact an ISP that's run maybe by the government or by some central company, but there could also be multiple ISPs. So if there are multiple ISPs, then the question becomes, how do they interconnect with one another? And there are two ways in which this can be done. The first one is through so-called IXPs, or Internet Exchange Points. Those are typically shared location, maybe located downtown Seattle or next to, let's say, next to the Dulles Airport in Washington, D.C., that are themselves neutral. They don't belong to any of the ISPs, so maybe they're run by some independent company, but different ISPs can connect to it, so they pay some fee, and they make sure that there is a link that connects to their network, and here they can exchange data. Or different ISPs may decide to create direct links between each other, so-called peering links, so the traffic that goes from one ISP to an access network that is serviced by another ISP can travel through this so-called peering link. Okay. Now, all of this is subject to a lot of negotiations and market forces, and also depends on the traffic, right? So that depends on how much traffic is actually sent by the customers of one ISP to another. There are regularly conflicts in this area, and these conflicts typically arise if there's a disagreement about who is bigger, right? Because traditionally the smaller ISP paid the larger ISP, but as ISPs grow in importance, that may change, right? And so generally the posturing here is that different ISPs say, well, I've been paying you, but I don't want to pay you anymore, and then the other ISP may sort of think, okay, so well, who gets hurt more if we cut this link, if we don't peer um, in this case, and then they typically arrive at some agreement. So you hear about these regularly in the news, or at least the specialized news in this area. But so far, it has not actually happened that somebody's access network was disconnected from the internet. But there's a lot of economic influence here. In this vein, what can also happen is if you have regional providers that support a lot of access networks and connect those, they may actually grow large and become of importance themselves. And one example here is Comcast, the company that runs more than half of the cable plants in the United States. They have become a very large ISP that has substantial influence themselves, and so they can sort of dictate peering agreements and traffic agreements with other ISPs. And as a third part, this is something that has happened in the last decade or so, and this is the emergence of large content provider networks. Google, Microsoft, Akamai is a company that runs so-called content distribution networks. Three examples. So Google serves a lot of data, and they certainly do not want to pay an upstream provider to carry this traffic, right? So what they've done instead is they built their own network, they bought their own fiber, built their own backbone, and they then either peer or connect to IXPs in different parts of the country in order to essentially they have become network providers themselves. So this is a trend that has occurred just during the last decade. So today's picture, the slide set, by the way, was just updated in a few days ago in April 2020 for the 8th edition of the Gross and Ross textbook. Okay, so the picture today is that where we have these networks by these large content providers such as Google. Um, we have traditional so-called tier one ISPs, right? These are these major ISPs that from the backbone of the internet they connect to everywhere. They typically peer with each other without asking for money. So they exchange traffic on a peer-to-peer basis connected to these IXPs. And then we have these emerging large regional ISPs. So Comcast here is the big one in this case. And then either these regional ISPs may serve customers directly or through a number of smaller access ISPs. This is a situation roughly that we see today, but this is something that is continually evolving as traffic changes, as new things are being developed, and so on. An example. So tier one, if you were to run an ISP and you wanted to buy access to the internet, you may approach Sprint as one tier one ISP, and they may show you this map that shows their network that they have, right? And it also shows where they have POPs, or points of presence. And these points of presence are places that you can connect your network to, and that connects to the remainder of Sprint's network, as well as connects to all the networks with which they are peering, um, and so there from there the entire internet can be reached. And this is an example of a network map that Sprint advertises here. Only one last example. That is the ISP that Virginia Tech has been connecting to for over 10 years now. It's an initiative called the Internet 2. And Internet 2 has its own backbone here as well. That's shown here with different connections across the country. And if you for example, connect to a computer that is in a different .edu domain, so public, private university in the United States or North America, then it's highly likely that your traffic would be carried on this Internet 2 network. Okay, this used to be a very at the time it was developed, it was faster than existing commercial providers. I don't know if that's still the case. I'm I'm not sure about that, but this is the backbone that is used for traffic that is exchanged between public or private educational institution and other partners in the United States.